Hey everybody, welcome to Computer Science A. We're going to be talking about recursion today. I'm Jill Westerland and I teach at Hoover High School in Hoover, Alabama.
And I am Rob Schultz. I teach at Bellbrook High School in Bellbrook, Ohio. As you can see, there's a little bit of distance between us. Again, hello from Bellbrook and from Hoover. And we also want to reach out and say hello to everybody that is tuning in with us right now. It still seems very surreal to me as a teacher in Bellbrook, Ohio, to be speaking to students all over the country and beyond. I mean, knowing that we have students in Canada and El Salvador and India that are following us right now. So welcome to everyone. We're glad that you are with us. Welcome to our virtual classroom. Looking at what's going on today, Mrs. Westerland is going to introduce us to recursion and recursive algorithms. Tomorrow and Friday, I'll be kind of picking up from there and looking at searching and sorting. We'll look at binary search tomorrow, and we'll look at merge sort and some other sorting algorithms on Friday. So we're starting to get to the beginning of the end. So for our warm-up, yesterday, one of the things that was suggested that you look at, in addition to the lesson resources from the CED, was free response question number 1 from the 2017 exam. And I know that it specifically says part A. If you only did part A, great. I went ahead and kind of worked up the solution set for part A and B, just so that we can go through them quickly together. Just so, again, a little more experience doing some free response stuff. What we suggest, if you haven't already, make sure you have a notebook or some paper and a pen or pencil so that, again, you can kind of take notes as we go. The other thing that you'll notice is that Mrs. Westerland has also been taking notes to model some of that good note-taking behavior. So I believe her notes are all shared out in the shared folders that we've made available. So make sure you're taking advantage of that. Make sure you're working on those note-taking skills. So let's jump in and look at free response question number 1 from 2017. Okay, so this question, the overview, I'm going to move my laptop a little bit out of the way. We are looking at a class called the digits class. It says the declaration of the digits class is shown below, and we are tasked with writing the constructor and writing one additional method for the digits class. So I want to make sure to point out 3 things that we've got. Okay, in the kind of shell of the digits class that they show us, the first thing they give us is a private array list of integers called digits list. So that's declared, but it's not destructed, it's not constructed. So one of the things that we're going to do is when we write the constructor where it says it's to be implemented in part A, we have to make sure that we actually construct our array list. The other thing we're going to do is we're going to create a method is strictly increasing that's going to return a Boolean value, and it says that's to be implemented in part B. So this is a 2-part question. Part A is going to be worth 5 points. Part B is going to be worth 4 points. So looking at part A, it says we have to write the constructor for the digits class, and it says the constructor initializes and fills digits list with all of the digits from the non-negative integer num. Now, again, I want to kind of unpack a little bit what it says, because the wording and the font is very important. It's telling us that we have to construct, we have to initialize our array list, and we have to fill it. It's also telling us that the number that we're going to be given is non-negative, which means 0 could also be included. So I'm going to move my little, no, you're okay. Part of my screen is being blocked here, so I'm going to slide this down a little bit. So it says the elements in digit list must be integer objects representing single digits. We're going to talk more about the difference between integer objects and primitive data types here in just a second. And it says that they have to appear in the same order as the digits in num. So in other words, if our value in num is 1, 2, 3, 4, then that means the elements in our digit list also have to be 1, 2, 3, 4 in that order. And we get 2 examples. And again, I want to point out, just like I did yesterday, that these examples are not specifically what we are coding for. In other words, we're not writing a specific digits class that handles only the numbers 15,704 and 0. These are strictly examples. Okay, so we want to make sure that our digits class will accommodate any number, any non-negative integer, not just these 2. Okay, so let's go ahead and take a quick look. So this is the code that was presented by the chief reader for the 2017 exam. Now, there are a couple things in there that you might not have seen before. okay? I want to focus specifically on new integer. Up until, I want to say, Java version 8, Mrs. Westerland made reference when we talked about array lists that array lists have to contain objects, and primitive data types aren't objects. In other words, if I want to take a primitive data type, an int or a double, and put it into an array list, I have to somehow convert that primitive to an object. So the process that we talk about, we use wrapper classes. Integer, spelled out with a capital I, is the wrapper class that corresponds to the int primitive type. So you could almost think of this as if I have something that I want to send to them, I could take what I want to send them, put it into a box, wrap it all up, and then once they get it, then they take the box, they unwrap it, and take out whatever I put inside. Well, that's basically how wrapping and unwrapping, or boxing and unboxing, I think it's referred to in the CED as boxing and unboxing. That's how that process works. In the past, we had to take a primitive, put it into an integer capital I object, and then we could put the object into an array list. So again, that's referred to as either wrapping or boxing. And that's what's displayed here, because as of 2017, that process was still valid content for the AP exam. So when the chief reader wrote the solution in 2017, because that was part of the AP subset, that notation was there. Go ahead and jump one more, if you would. There we go. So now if you look under topic 2.8 in the CED, auto-boxing is the automatic conversion that takes place when we take a primitive type and automatically convert it to its corresponding wrapper. So in this case, this is what the code would look like if we use or take advantage of that auto boxing. Okay, I don't necessarily have to say new integer 0 or new integer num modulo 10. This would be perfectly acceptable, but I wanted to make note of that so that when you go out and look at the chief reader's canonical solution and the scoring guidelines, and you see that notation, that you understand what that is. This is the first year that auto boxing and unboxing is recognized on the AP exam. So boxing and unboxing is not something that would be tested on. So this, for this year's exam, this is what a typical solution would look like. For the sake of being consistent, so that you would recognize it when you saw it, no, you're okay. I went ahead and kept the solution with the way it was written in 2017. So I wanted to make sure that that was kind of made note of. Okay. All right, so we said part A was worth 5 points. We have to construct digit list. We have to identify a digit in num. Okay, to get a point, we just have to identify a digit. We get another point if we add at least one identified digit to a list. And then if we add all of the identified digits to a list in the context of a loop, that's our 4th point. And finally, if on exit, our constructor, on exit of our constructor, digit list contains all and only the digits of num in the correct order. Okay, so let's look at our solution and work through one at a time. The very first line, we say digit list equals new array list integer. So we are constructing digit list. That is okay. So there's our first point. The second point, do we identify a digit in num? Yes, we do with num modulo 10. If you think about what modulo 10 does, modulo gives us the remainder of a division problem. So if I have, for example, the number 369, if I divide by 10, remember in Java, an int divided by an int gives us an int. So 369 divided by 10 will give us 36 with a remainder of 9, and that's where the modulo comes from. So by using num modulo 10, we're identifying the last digit in our number. Okay, we then go on and we add that one identified digit to a list. So we use digit list.add. We're adding it specifically at position 0 using that add method that we talked about yesterday. And we're saying that specifically at position 0, at the front of our list, we want to add whatever the identified value is. And then we do go through in the context of a loop, and we add all of the identified digits to the list. And because we're taking them in reverse order, we're taking the number off the back, the ones digit, I guess you could say. Every time we do num modulo 10, we're pulling the nums digit, the ones digit, and we're adding it at the front of the list. So first I'll pull the 9, and then I'll insert the 6 in front of it, and then I'll insert the 3 in front of it if my number happens to be 369. Okay. And then finally, because we're doing everything correctly, On exit, digit list will contain all and only the digits of num in the correct order. And remember, we had that one example where it showed us 0. Well, if we just look at our while loop, if num happens to be 0, then 0 won't be greater than 0, which means it'll never actually go through the while loop, which means nothing will be added to the list. So we have to throw that one extra little if statement at the beginning, just on the off chance that the num that could be passed in is 0. If num happens to be 0, great. We'll create digit list, we'll add 0 to it, and then we'll skip the while loop so we don't put anything else in. And that way we're covered. We have every possible non-negative integer that we could have thrown at us. Okay, part B goes on and it says that we have to write the method is strictly increasing. The method returns true if the elements of digit list appear in strictly increasing order, otherwise it returns false. And it goes on to specify that a list is considered strictly increasing if each element after the first is greater than but not equal to the preceding element. So we want to look at each digit in our number and make sure that it is specifically greater than but not greater than or equal to the number that comes before it. So here's our canonical solution. Again, there's some extra little things in there that you might not be familiar with. If you look specifically at int value, well, this is the unboxing part. This is assuming that I just received a gift from a friend. Int value is the process of opening the box and taking out the primitive integer that's inside, okay? Again, if you could go ahead and go one more for me.
Yeah.
If you look at topic 2.8, unboxing is the automatic conversion that the Java compiler makes from the wrapper class to the primitive type. So this basically unwraps or unboxes that object for us. We don't have to worry about getting int value. We automatically know it's an array list of integers. We've already specified that it's integers. So if I say get I, it's automatically going to give me the primitive that's in that spot, in that object. Okay. Nope, go ahead.
Oh, go ahead.
Yep, thank you. So we already covered the first 5 points. So is strictly increasing is worth 4 points. We have to compare at least one identified consecutive pair of digit list elements. We have to determine if a consecutive pair of digit list is out of order in the context of a traversal. We have to compare all of the necessary consecutive pairs of elements with no bounds errors. And then we have to return true if and only if all consecutive pairs of elements are in order, and it will return false otherwise. Now, I'll tell you that in the past, when I've done this specific problem with my students, every year, there were some that questioned the IFF. IFF simply means if and only if, and the chief reader that year was adamant that he wanted that specific wording. So that's why that's there. That is not a typo. So our first point, we compare at least one identified consecutive pair of digit list elements. You notice we get digit list, we have digit list.getI and we have digit list.getI plus 1. So there's our consecutive pair of elements, and there is a comparison in between them. Notice it doesn't say it has to be a correct comparison. It just says that we have to compare them in some way. So if I had greater than, if I had less than, if I had not equal to, if I'm comparing them in any way, we would earn that point as long as I'm using a consecutive pair. We have to determine if a consecutive pair of digit list is out of order inside the context of a traversal. So this is where we're checking to make sure that we are specifically using greater than or equal to, and that we are going through within the traversal of digit list to make sure that our consecutive pair is in the correct order. We compare all of the necessary consecutive pairs of elements with no bounds errors. So notice that our for loop goes from 0 to digit list.size minus 1. We have to make sure that we stop at size minus 1 because we're comparing I to I plus 1. So we're comparing 0 to 1, 1 to 2, 2 to 3, 3 to 4, until we get to the second to last element. We're going to compare it to the last element, and then we stop at that point. If we go one more, then we're going to compare the last element to something that's out of bounds, and we'll throw a bounds error. So we are accommodating the no bounds errors rule, and we earn that point. And then finally, we return true if and only if all consecutive pairs of elements are in order. We return false otherwise. If at any point inside our for loop that if statement says that we have a problem, if there's any time that if returns true, in other words, our value is greater than or equal to the value behind it, we immediately stop and we return false. If we get all the way through the for loop and that if statement has never triggered the return false, we return true. So we return true if and only if all consecutive pairs of elements are in the correct order, and otherwise we return false. One more thing with this one. Remember at the beginning when we were looking at the problem description and I said that the wording and the font is very, very specific, okay? Digit list is in Courier New for a reason, okay? They're telling us that because
Sorry,
no, you're okay.
Because
Because digit list is our declared array list and all of the questions, or I'm not gonna say all, but most of the points on the rubric specifically refer to digit list. If you accidentally went through and created a new array list called mylist or dig list or digits, or I mean, anything other than digit list, looking at the points on the rubric, that would be a lot of points that were lost simply because you misnamed your array list. Okay, so the decision that was made was rather than dock you 4 or 5 or 6 points because it said specifically in the rubric that you needed to use digit list, if you did everything correctly and you only made the mistake of declaring an array list that had a different name or constructing an array list with a different name, then you would lose 2 points for having a confused identifier. But then because you used it correctly, assuming that you were using digit list, then all of the other points would become valid again. So the decision was made to make this a question-specific penalty, so that you wouldn't lose a ton of points for a misnamed identifier. You would only lose 2. So that was the question-specific penalty for this question.
Fabulous. I think the big thing I've gotten out of yesterday and today, and I think I told my class this, maybe, is you got to watch for that font. When you see Courier New in the free response questions, it needs to be highlighted, underlined, a mental note, something.
Yeah,
You know, it's important.
That's done very, very purposefully because
Mhm.
there's a specific intent to that. You know, these questions are written with the wording very, very specifically put into place and the font to identify specific things that absolutely have to be there as part of
Yeah,
your
it's almost
solution.
like a bag of puzzle pieces, and you pour
Yeah,
them out on the table, and some of them need to be noticed because they're the edge pieces, and maybe for us, that's our Courier New.
yeah,
So,
it's a good way
anyway,
to think of it.
I like that. I love listening to Mr. Schultz explain the free response.
Thank you.
So, now we're gonna switch gears to recursion and start our one of 3 days, talking about recursion, and in order to understand the code you're going to look at with recursion, you need to be able to identify a one-way selection, two-way selection, and a method with parameters. And this should be easy kind of stuff from Unit 3. And you've done parameters and methods all year long. So I've got just a couple of little dog-themed selection for you to look at. So this is one-way selection where we only have an if. And if this condition proves true, the programming statement that's under it will be enacted or invoked. And if it's not, it just won't happen. And those are the two things that happen. And there would be the output. Here we have also one-way selection, but for this one, I want you to notice that there are brackets now. If you have more than 2 lines of a programming statement, they need to be enclosed in brackets. And you might work with an editor that lets you get away with certain things. Sometimes, maybe not. So just kind of watch for that. Watch for the number of lines that you have. All right, here we have another two-way selection. And it comes out and goes down to the false condition because treats has got to be greater than 1, and it's not. All right, so now we have kind of all 3 things happening. We've got a method happening down here, get treat, that takes in 2 parameters, and it's called a couple of times. And here's its output. And this should be super easy for y'all. So now we've got a little quiz question that's not related to dogs. So 2 little questions. What type of selection is used in this problem? Is it one-way selection or two-way selection? And how many methods are called? I mean, how many method calls are made? So there's your answer to number 1. It's two-way selection because if the test score is greater than or equal to 93, it's going to invoke the first section, the if part. Otherwise, it's going to hop down to the else, and it's going to invoke the else portion. And we have 3 method calls with 3 wonderful students in a class.
Nice shout out.
That's right. So that's your background. So now let's talk about recursion. And we will look at some basic recursion, a little bit of fun recursion, and then tomorrow and Friday, Mr. Schultz is going to continue the discussion on into recursive sorting and searching. Recursion is a process where a method calls itself. So that's part of why I set you up by looking at method calls, because that's what you're going to be kind of zeroing in on a little bit to identify the recursion in an algorithm. Recursive methods have to have a base case. So, you know, like with a for loop, you have a counter that controls your loop. Otherwise, it's going to be an infinite loop if you don't have a counter that's going to control the loop. In a recursive method, it's going to look for a base case to cause it to stop or catch it so that it'll know how to end. Otherwise, you're going to have, you know, the same thing happening. It's going to go on forever. We'll look at an example of that. Each recursive call has its own local variables or formal parameters. Parameters catch the progress of the recursive process, like I just said, similar to your loop control. There are some algorithms that are easier to write recursively than iteratively. Many can be written both ways, but some are more elegant and more efficient in one style or the other. And so that's part of what we'll be looking at in the next couple of days is how they look. And I'm going to show you some both ways today, but our examples today are tiny and, you know, I don't know, just sort of math-based a little bit compared to the sorting and the searching that we'll see. Most recursive calls can be replicated through iteration, but you do not have to worry about having to write recursion. So recursion is unit 10 of the CSA course. So we've made it to the very end of the course with unit 10 and recursion. You will hear about it in college, especially if you're an engineering or a CS major. You probably will have to write recursive code in college if you're any of those majors. I would, you know, go to the bank on that. But you don't have to write recursion in CSA course. However, you can use it on your free response, you know, writings that you do to answer the prompts. If you like it, if you're comfortable with it, and if you feel like that it fits the solution that you want to write for your code. Recursion can be used to traverse any of the string, array, or array list objects. So that's what we'll be looking at. Y'all have written an array list this week. And like, remember on Monday, you built an array list, and on Tuesday, you added objects to your array. And so our hope is that when we get into Thursday, Friday, you're going to add the recursive sorting and searching methods to the array that you have. So here are some examples. These are the top 3 that I just kind of, I don't know, maybe everybody thinks these 3, or I do anyway. Greatest common factor, factorial, palindrome. Palindrome's a word, you know, that means the same thing forward and backward, or it's spelled the same, reads the same. Linear search, binary search, and merge sort are some examples of classic recursive algorithms that we're going to look at this week. We may look at linear search also in the future when we come back to arrays, but for today, I'm going to show you examples of the top 3 bullets, knowing that we're coming to these others later. So before we look at some code, I want to unpack a little bit base case for you. The phrase is used to refer to the exit that stops the recursive process. So that's what it's going to check for to make the recursion not happen any longer. Without a base case, you're going to get a Stack Overflow error. And the base case will usually return a value, and you'll see that in the code. It might return an empty space bar. It might return a 1. You know, you're the programmer. You can decide what it returns. So this is a basic recursive problem. I've given it to you actually lines 10 through 14 are a method that is a for loop. Lines 16 down to 23 are a recursive procedure that does the same thing. So line number 18 is your check, and line number 21 is the recursive call where it's calling itself. So notice that within count up to, it's calling count up to. So that's what you're looking for with a recursive algorithm, is when it calls itself. Here's the output of this code, and like I have noted at the top, today what I decided to do is give you the JDoodle code right here with the problem. I might not do that every time. It's also in the folder for you, but as you're looking at these simple little problems, you might have fun going over to JDoodle and playing with the code, and you can grab it from there and move it back to something else. I probably put it in the folder as source code as well. So you can plug in difference. You can see that my parameter values, I wanted it to just count from 1 to 10. You could put in 1 to 1,000, whatever number you want it to do. Here's a bad example, an example without a base case. Same problem, count up 1, count up 2. What do you notice that's different about this one? Look at lines 7 and 9. We're missing parameters. So what happens with this problem is the recursive problem goes on and on until the stack overflows. And I was a little paranoid when I was writing this up to put it in JGrass, because I thought, I don't know what's going to happen to my computer or my JGrass. So I got it over to JDoodle. I thought, well, if I lock up my browser, it won't be as bad. And so, I didn't feel as paranoid about that. So play with these kinds of things, maybe on the cloud-based programs, unless you're really brave, because you're not on a school computer right now, you're at home. So you don't want to be doing sketchy stuff on your home computer. I didn't give you the code for this one because it's a bad example and I don't want to lead you down a bad path. Just take our word. All right, greatest common factor. So this is Euclid's algorithm, and you're familiar with this from math for years back. And I've got num1 and num2 are my two variables. I just plugged in numbers there. There's no magic to them. You could make life hard and put in a prime number and see what happens with that. But I just did numbers that I felt like would give me some kind of a result when I ran it. So the recursive function is going to take those two items, find their remainder between the two using modulus, and then give us the result. So there's our base case, and there's our recursive call. So when the remainder exactly equals 0, we've got to have found the last call that we can make. So play around with this code, plug in other numbers. This common factor would be 15 between the two numbers that I threw in. Factorial is really nice in recursion, and I used a pretty simple number here so that I would get a simple number. So do the math here. What is 4 factorial? You know the answer, right? So let's look at the call. So this could have been when num equals 0, could have been when num equals 1, but it's better to check for less than 0 or 1 so that we don't fall into a trap with a negative number. But it would work similarly with num equals 1. It would return 1, because that's really when factorial is going to stop, is when you get to 1, you're finished. So 4 times 3 times 2 times 1 is going to give us you see the lines that I pointed out. Oops, and you're going to get 24. I'll sit right there for a second so that you can look at that JDoodle link. Because this is one I think you're going to want to plug in larger numbers and let it do the math for you. All right, Palindrome Checker. So this is a fun thing to do in class. And I have this shown to you in recursion and in for loop version. This particular code works really well to use the char at option that is a function of the string class. So that's what you see here. It's comparing the character at 0 in our string to the character at the end with -1. And then it's going to continue to do that working inward to see if the word is a palindrome. So here are some others. And I want to talk about why some of them are palindromes. Like, why is this Hannah a palindrome and the other Hannah not a palindrome? We, with our human inference, would say that this Hannah is also, the second one is also a palindrome, because we're inferring that lowercase h is the same thing as uppercase h. And you'll notice in my code, I put the strings in all uppercase. So you might be thinking, I hope you're thinking, what would you do to work around this? What could you add to this method to make this problem not happen? You could pull the method to convert to upper or to lower so that you stripped it down and you wouldn't have that problem. And that's a good solution. It's not what I chose to do because I wanted to kind of make this point that this goes all the way back to very beginning computer. You might have done this in middle school or the beginning of maybe the CS Principles course if you took it. Computers only do what we tell them to do. So if your teacher did, the teacher's the robot and you tell them to walk into the wall, or maybe your teacher did peanut butter and jelly sandwich. There's a lot of different ways to teach that a computer's only going to do what you tell it to do. This is one of those times. So alphabet letters are encoded, and I looked it up, and that the Java is pulling from UTF-16, which is a 2-byte system, similar to ASCII, but ASCII uses 1 byte. So essentially, there's a numeric value that's encoded to every alphabet letter. So lowercase h is like 104 or 102, and uppercase h is, I think, 72. So when the computer reads this, when that string is evaluated, it's looking at a numeric value for the alphabet letter, and that's why it's not able to make that human inference. So I hope that's clear. And you definitely are going to want to go, hopefully, and play with the palindrome checker code, because I think that you'll be able to do some fun things and check. There's a lot of fun little palindrome, like nurses run is a palindrome. I don't know. You can look it up, but there's a lot of fun
Able
ones.
was I ere I saw Elba.
Oh, say
It's
it
one of my
again.
favorites. Able was I ere I saw Elba.
Oh my goodness, it's a good one. Able was I ere I saw Elba.
Yeah.
And you could create your own. So go play with these. You also could add user input to it so that you typed in a word and it checked your word. I didn't go there with this sample, but that might be something you've done in your classroom this year. And if you haven't, I want to encourage you to try. So here's another thing that we do in my class sometimes with recursion on the left side. Not the fractal trees. Fractal trees is classic recursion, and you'll hear people talk about fractal trees. And if you took geometry maybe in 9th, 10th grade, you might have seen Sierpinski's triangle, where the triangle continually splits into 3 more triangles, and those triangles split into 3 more triangles. This is a little bit of the same type thing. It's a graphics lab that I got from a man in Texas, and I colored it up this morning in spring colors because it's easier to see the recursion happen. And I'm going to play the video so that you can watch what's happening here. It'll take it a second for it to start redrawing, but it's going to start in the middle with the large pink square, and then it's going to start drawing out. It happens so quickly in the northwest corner. Then it draws the southwest corner, northeast, southeast, but it's continually drawing smaller and smaller shapes, always out to the northwest. And so the colors really help you see which direction the shapes are going in. I've given you this code. It's called lab_graphic recursion in the Google Drive folder. so that you can play with this. I don't know that this would work out on a cloud browser. It might. I didn't try it there. You're probably going to want to put it in an editor. And you can, of course, change your colors to be different than my colors. You could do, and these are not hard-coded object colors. So you got two options if you want to have some fun with this recursive project. You can look up more colors in Java. What colors does Java know? I'm not going to tell you the answer. You'll see there that I've used just basic colors, so you can replicate mine. Or you can get really fancy and look up how Java lets you create your own colors using red, green, blue, and create color objects that are calling from red, green, blue values between 0 and 255, and make your own colors and have kind of something fun and fancy. You could also add another drawing on top of the center option. Now, fractal tree, you can kind of see what's happening over here. It starts with one trunk of the tree. So at first it's going to draw this, and then it's going to split two directions and go two different angles. And then you'll notice every time it picks up, that singular branch continues to split. And you'll find fractal code to draw trees and snowflakes all over the internet. All of those are recursive programs. I don't know what you would, you can draw a lot of different things, but you see a lot of trees and snowflakes, but people draw some really cool things with that. So I wanted to just show you these because they're interesting. All right, let's kind of wrap up our Recursion 101 lesson today. Here are the 5 big points. Recursion is a method that calls itself, so you're always looking for a method. It needs to have a base case, or you're going to have a problem that will result in Stack Overflow. Each recursive call should have its own formal parameters, and the parameter values are going to capture the progress or trace the call. And the algorithms, sometimes there are algorithms that are easier to write recursively that work more elegantly, more efficiently. And you don't have to write recursion, but if you like it and you know how and you want to, you can. And we'll talk later about some different things that might fall into the category that once you see the searches and the sorts, you might think of some things as we go through the next few weeks that, oh, that could be written recursively. That might be an easier way to write that. Or you just stick with a traditional iterative for loop or while loop and life goes on. But you will hear about this in college for sure. 2 big words we talked about a lot today, recursion and base case. Tomorrow, I've given y'all this little teaser of, there's a lot of cool videos about that show you pictures, graphical representations of searching and sorting data. And so you're going to see that over the next couple of days.
I think my students' favorite video is when we look at the dancers that demonstrate the different sorting algorithms by dancing. Yeah. I actually had a group of students that were going to try and replicate that for some extra credit for a talent show, which was unfortunately canceled because of everything going on.
Oh, they should go ahead and do it. Well, they can't do it now because
no, they can't,
we're all sequestered. So
yeah. I did want to share before we got to the power up. I thought of this while you were presenting. My favorite example of recursion is a KitKat bar. I love KitKat bars. And for those that don't know how KitKat bars are made, when they come to the end of the production process and they're about to be packaged, if there's a KitKat bar that isn't perfectly made, it's pushed off to the side and all of the imperfect KitKat bars are taken back to the beginning of the process where they're put into a vat, they're mushed up to make the pulp that's used to fill KitKat bars. So every time you eat a KitKat bar, you're actually eating a KitKat bar that has been filled with KitKat bars, which were filled with KitKat bars, which were filled with KitKat bars,
oh wow,
KitKat bars, and so on and so on and so on. So yeah, that's so cool. Somebody shared that with me a while ago, and I thought of it while you were presenting, and so yeah, that's one of my favorite recursion examples is a KitKat bar. Yeah.
I love that. Kind of like a cake pop almost.
Yeah.
I mean, you know, sort of. All right, well, take it away, Mr. Schultz.
Okay, so as Mrs. Westerland said, we're going to move on tomorrow and we're going to dig deeper into recursion. We're going to look specifically at, I want to say it's unit 10, section 2 or 10.2 in the CED, which gets into searching and sorting algorithms. So tomorrow we are going to look at specifically binary search, the recursive implementation of binary search, and then on Friday we're going to look at some sorting algorithms, and we're going to look specifically at merge sort. So as you think about the resources for tonight, Mrs. Westerland has put together a power-up that includes some lesson resources from the CED, some things on Runestone and PracticeSet and CodingBat. CodingBat, I'll be honest, is one of my favorites. I use that in class all the time. And it might not be a bad idea just to go out and do a quick look at some of the different algorithms that there are for searching. Tomorrow, when we start out, it would be helpful if you had a little bit of a background in what linear search is, and maybe even have seen the iterative implementation of binary search. We'll go through both of those, but if you've seen those before, it might make things a little more understandable as we go. So that would be kind of the bonus to your homework tonight. As always, we wanted to make sure we threw in our CSA show and share. We have some students that have been following along and have submitted code or submitted pictures of their pets. So we've got Claire in Fenton, Michigan, and Maddie from Connecticut remind us to smile like.
To smile like when you try your code for the first time and it actually works.
I gotcha.
This was a meme, and it was a Pikachu, but I was paranoid about copyright, so
I gotcha.
I just what do you call it? Mismatched.
Yeah,
I don't know.
You go. Yeah,
whatever.
That works. So we've got Mrs. Keller's Apex from Friendship High School in Miles, North Carolina. We've got Ms. Blasco's Spaz from Great Mills High School in MD is Maryland, right?
I think so. And you, yeah, Maryland, but you wrote about Spaz yesterday.
Yeah, Spaz was actually one of the pets that I used in my example yesterday. Right. We've got Naida, I'm afraid I'm going to pronounce that wrong, from Paint Branch High School in Maryland, and we've got Miss LaBarge Jackson from Pittsford Schools in New York. So thank you all for tuning in and kind of following along with what we're doing. I also wanted to make a big shout out to Justin from Toronto and to P from Mechanicsburg, Pennsylvania, because yesterday I kind of threw out a little prompt to see if anybody would bite, see if anybody would take the bait and go out and do some research. And I did have a couple students that emailed back that said that they did. If you were with us yesterday, I threw out just the idea to go out and maybe do a little research to figure out why the overloaded methods in the array list class returned what they did. One of them returns void and the other one returns Boolean. And we did have two students that went out and researched that. Maybe more of you researched it, but we heard from two. And so gold started Justin from Toronto, Ontario, and to P from Mechanicsburg, Pennsylvania, for actually looking up the answers to those.
No, and they're really thoughtful.
Yeah.
Well explained. And what they did is they put the answers in documents and uploaded those to the 2-bits section. And there's somebody, maybe a teacher, who wants to turn in some more resources. So if you'll stick them in a document, PDF or otherwise, and upload them through this 2-bits form, that's the best way to get some more resources added. Might be Yvette, if I remember correctly. So kudos to you guys. Yep. We would give you candy, but we can't because we're too far away.
And as always, Floppy from Manhattan says, submit your 2 bits of CSA smiles. Check out our bit.ly form. We have bit.ly/my2bits. Make sure that you're sharing pictures of your pets, maybe some things you've done from GarageBand or EarSketch or something, maybe an artifact that you did in the AP Principles class, some original photography, an original meme, something to have a little fun that we can maybe work into some of our slides and share some of the things that you share with us.
That's right.
As always, College Board wants to know if you are having problems with if you are having access problems to the internet or to a device, College Board wants to be able to help you out with that. So if you or another student is in that situation, make sure you go to cb.org/tech to let them know, and then College Board will try to help you out with that. And that's it for today. We appreciate everybody tuning in, and it's nice to be with everybody again, even if we're together apart. At least we're together in this.
We're not alone.
Yeah, so it's nice to know that you are all here with us, and we look forward to seeing you again tomorrow.
Bye, everybody.
Everybody have a great day.